Hello everyone, welcome back to Digital Electronics. I have here IC4060. This is CD4060. This is CMOS IC, and this is a 14-bit counter. Then since it has a 14-bit counter, it is a 14-bit counter. It has 16,384 combinations of counting. So this is the diagram. This IC have 16 pins. Then also it has a built-in crystal oscillator inside, and we just have to add additional component outside here, like the R1 and C1, to control the frequency of the internal oscillator. So by adding R1 and C1, you can set a frequency for the oscillator inside. So there is a formula for RC. The formula for RC, like computing the frequency of the oscillator inside of this IC, is frequency, or F, is equals to 1 over 2.5 times R1 C1. 2.5 is constant, and R1 and C1 is depending on how much value you assign to these two components. So in this case, we assigned for R1, which is 68 kilo ohms, and C1 is 0.01 microfarad, or that is 103 picofarad. So that's in microfarad, that is 0.01. Then we have to convert also 68K to ohms, because everything must be converted to the base unit, which is resistor for ohms and capacitor for farad. So we have to convert 68 kilo ohms, so that is 68,000 ohms, and from 103 picofarad then to microfarad is 0.01, then convert again to farad, which is 0.0000701 farad, so that all the units must be same in the base unit. So 2.5 times 68,000 ohms times 0.0000001 farad. So the frequency is 588.2 hertz. So that's approximately, it's not really, we cannot say that this is really a perfect frequency that the oscillator can produce inside, since this resistor has a tolerance, capacitor has a tolerance. So these are not a perfect value for the resistance, and not perfect value for the capacitance, and so therefore we cannot say that this is also a perfect frequency that we can get in inside oscillator. So that's more or less 588.2 kilohertz, hertz rather, 588.2 hertz. Now by this time, so we connect, so that one, R1 C1. So this one is another resistor, additional is R equals to 1 kilo ohms, but not doesn't contribute to the control of the frequency of the oscillator inside. So this is just an additional, because this is part of these three pins as as external components to set the frequency of the internal oscillator. So by this time again, we got 588.2 hertz out of these two values that we use. Now, this is the output. So actually, this IC has 10 outputs. So from 1 to 7, then 13, 14, and 15. So that's here. Actually, we tried to compute the frequency of its output. So based on our Q7 is 56.8 hertz. That's based on our oscilloscope. See, look at here. So we connect at pin 7, Q4, that's Q4. The frequency is 56.8 hertz. That's from the oscilloscope reading. Then because we connect our probe here at pin 7, and that is again Q4 56.8 hertz. So let's see here. If we press measure, so measure the output. Okay, so look at that. The frequency is 56.4. That's actually fluctuating. 56, 56.3, 0.4, 0.6 sometimes. So maybe average of 56.4. Also, I write here 56.8. So that's the frequency for Q4 pin number 7 with this oscillating frequency or oscillator frequency inside this chip. Yeah, and Q5, 6, 7, so on and so forth. These are the different frequencies. So for Q5, 28 hertz, 14 hertz, 7 hertz, 3.5, 3.57 hertz, 1.76, 0.888, 0.22, 0.11, 0.05. So, like for example, we can relate this one. Like for example, this Q4 pin number 7 is which has a higher frequency, 56.8 hertz. So, and the bottom here is Q14 pin number 3 is the lowest frequency is 0.05 hertz. Just looking at the display, this is a pin 7. No, this is a pin see, yeah, this is pin 7. This is pin 7, the first display. That's pin 7. As you can see, as if it doesn't on and off anymore. It's like constantly turn on. See, because of this higher frequency, you cannot see that this display is turning on and off because it has a continuous frequency. So like this, this one. Okay, so that's because of that frequency. So you cannot notice that this display is turning on and off. And the very low frequency here is Q14.05 hertz. Here, see, it when it is turned on, then yeah, off, then it takes like maybe 10 seconds to turn on again. See, on, then off. Okay, so it's around 20 seconds or more or less, because we computed the Q4 time to on this Q4, and the time is 1 over frequency. Then the frequency we got from oscilloscope is 56.8 hertz average. Then we use that one here in our computation, that is 0.0176 seconds. This output Q4 will turn on and off, so it's very fast. That's why you cannot notice that this display is turning on and off, because of this frequency, and the time is very fast, no? And the bottom here, the lowest frequency, so 1 over 0.05 hertz, then the time is 20 seconds more or less based on our computation. But look at here, this one, this yeah, on, then on, off. So that's actually, I put a timer on this display, but that's like around 10 seconds. So but the computation is 20 seconds. But we, since again we're not really sure that this frequency is really fixed or perfect frequency, because again our components has a tolerance. But maybe in real application, like applying this IC in commercial circuits, so maybe they use more precise components that will have an output. Or actually, this RC here, you can replace this with a fixed crystal oscillator. Like for example, I will show you the crystal oscillator. If you remember in AM/FM tuner, this one, this yellow component, this one is a fixed oscillator, and this blue also is a fixed oscillator for FM, and this is a fixed oscillator for AM. This 455 kilohertz oscillator, and this is a 10.7 megahertz oscillator. So if you connect this to these pins, instead of using RC combinations, then maybe for sure you can get the exact frequency. So that's why we cannot get the exact time. This Q14 and even this Q4 that we got an example, these two. Then when the time this Q14 will on and off, and also the Q4, so the time is for the Q4 is 0.0176 seconds, and for Q14 is, we just got the highest frequency and the lowest frequency. Okay, so again, this is the display. So The resistor here is a limiting resistor to prevent our display in overcurrent or over voltage, because this is a 5 volts and this display needs only like 2.8 volts, 2.5 2.8 volts. So we need a 220 ohms resistor to limit the current and having a voltage drop as well. So yeah, another application of this is they use this IC in as a timer, you know, because this is a counter, so they can use this as counter, and every output maybe they connect this to any other circuits, you know, that will trigger the on and off of those circuits. Okay, so that's CD4060 14 bits binary counter. So again, that's the output. So if we try this, the probe connect to, look at the output. It is actually a binary signal having a frequency again of 56.8 more or less hertz. We try in other pin. See, we try in pin number 6. Pin number 6. Pin number 6 is Q7, having a frequency of 7 hertz. So we'll see. So look at that. The signal change. We adjust here the time. See? And we try to get the frequency, measure. Okay. So we get a 7.07 hertz. So here we recorded 7 hertz for Q7, pin number 6. So here is frequency 7.0607, fluctuating, so more or less 7. Okay. See, so that's the output of Q7. Okay, so that's all for now, guys. Next time we'll have lots of ICs to introduce to you guys. Like actually I have lots of ICs here, lots of components. Okay, so I will show to you one by one every component. These are lots. So lots, yeah. So different capacitor, resistors, ICs, transistors. Okay. This is for our succeeding projects. So because we need different values of resistors, different values of transistor, capacitor, different numbers of transistors. Okay, ICs. So look at that, guys. This is our work bins here. Okay, it's like a shop. Okay, that's all for now, guys. Bye.